This video, we're going to start our discussion of linear models, that is, applications of linear differential equations. We'll start off with growth and decay models, usually population growth. You could also have mortality rates and things like that. And so let's go ahead and let's look at this first example here. I'm just going to read the problem to you. The population of a community is known to increase at a rate proportional to the number of people present at time t. So that tells me that dp dt is proportional to p, which then tells me that dp dt is equal to kp, and k is my constant of proportionality here. So then we can rewrite this as dp dt minus kp is equal to 0. We have a linear equation there where my p of t, not this p, but this coefficient here that we normally call p, is going to be a negative k. So my mu is going to be e to the integral of negative k dt. So that equals e to the negative kt. We'll write this as d dt of p times e to the negative kt is equal to 0 times e to the negative kt is going to be 0. When we take the integral, the antiderivative, this is going to be a constant c, so p times e to the negative kt is equal to some constant of integration c, because the derivative of any constant is 0. Solving for p of t, we get that it's c e to the kt. We're given some additional information in the problem now, that the initial population, p at time 0, we're going to call that p0, p naught, like that, and that it doubles in 5 years. So p of 5 is equal to 2 p naught, and we want to know time to triple. And we want to know time to quadruple. Okay, so first things first is that we know that p of 0 is going to be equal to c e to the 0, going to be c times 1 is c. We know that p of 0 was p naught, so we'll come back and write our equation here. P of t is equal to p naught e to the kt. And we're going to see that that's just going to work out with our population growth models. We're going to work out this way, but since it's differential equations, we're going to go through the process each time to come up with that equation instead of just using that. And so now our next piece of information that we can use is that p of 5 is equal to p naught e to the 5k. And we know that that's going to be equal to 2 p naught. So p naught is going to cancel out here, and e to the 5k is going to be equal to 2. And let's solve this. So 5k is equal to ln of 2, and k is equal to 1/5 ln of 2, or is equal to ln of the 5th root of 2, or I could write that as ln of 2 to the 1/5. I'm going to use that last form there so I can get an exact answer here for what my equation is. So p of t is going to be p naught e and my k value is ln of 2 to the 1/5 times t. When I raise a power to a power, I multiply the exponent. So I'm going to say all of that is to the t power, and e to the ln, they're going to undo one another. So this is going to be the same as p naught times 2 to the, and then 1/5 raised to the t, or p naught times 2 to the t over 5. Just trying to keep this as exact as possible here. So now we ask for time to triple. And so that's going to be p naught times 2 to the t over 5 is going to be equal to 3. So 3p naught, so 2 to the t over 5 is equal to 3. So this is going to be 2 to the t is equal to 3 to the 5th. And then we have, take the log base 2 of both sides. T is going to be equal to exactly log base 2 of 3 to the 5th, or t is equal to 5 times log base 2 of 3. So we can figure out that that's approximately 7.9 years when we round to the nearest tenth of a year. Have your calculator handy for these problems so you can verify this. Next question was, how long does it take for it to quadruple? Again, the p naughts will go away there. And so 2 to the t over 5 is equal to 2 to the second here. So by our 1-to-1 property, t over 5 is equal to 2, and t is exactly equal to 10 years here. So that is our first example here with growth and decay, specifically population models here. Let's go ahead and look at our next example. So the population of a town grows at a rate proportional to the population present at time t. So again, we're saying dp dt is proportional to the population that's present. More people present, the population rate, the rate of growth is faster. So dp dt is equal to kp again. So dp dt minus kp is equal to 0. Mu is equal to e to the integral negative k dt is equal to e to the negative kt. So we have d dt times p times e to the negative kt is equal to 0. P e to the negative kt is equal to c. P is equal to c e to the kt. And then we have again that P, now they tell us the initial population here. P at time 0 is equal to 500. So we're going to have P of 0 is equal to C e to the 0 is equal to C is equal to 500. So P of T is equal to 500 e to the kt. Then they tell us that it's increased by 15% in 10 years. So P of 10 is equal to 500 e to the k t 1.15 times 500 is really what that tells me. So P of 1.15, 15%. So that is equal to, let's see, 115 times 5, 25, 575. So, all right. And so that is equal to 500 e to the 10k is equal to 575. E to the 10k is equal to 575 divided by 100 is 1.15. 10k is equal to ln of 1.15. And k is equal to 1/10 ln of 1.15. Let's go ahead and just use that exact number and get our equation again here. So P of t is exactly equal to 500 e to the ln of 1.15, and that's going to be raised to the 1/10 times t, so that's t over 10 there. So this is going to be 500 times 1.15 to the t over 10. There's my exact equation. Now they ask me what's going to happen in 30 years. So P of 30 is equal to 500 times 1.15 to the 30 over 10. 30 over 10 reduces to be 3. And I have done that earlier and found out that this is approximately 760 people. Remember, applications here, we're going to want to include units, and we also want to consider the context of the problem here, that we're dealing with people, so we don't want to answer in a fraction of a person, something like that. It's okay to have a, it's kind of okay to have a fraction of a person with a growth rate, though I'm also going to be asked what's dp dt at t equals 30. So let's go back to our equation here that dp dt is equal to kp. And so dp dt is equal to k is 1/10 ln of 1.15 times, and then the p, that was an approximation there, so let me just throw in the exact value here, 500 times 1.15 to the third. If you go ahead and round this to the nearest person per year, you're going to get that that's approximately 11 people per year. So again, include your units in these application problems, and that's it for these growth models. I'm going to come back next time and we'll talk about some radioactive decay problems, some half-life problems, and some carbon dating problems. Those are all related topics. So I'll do a few examples of those. They're also in this growth and decay big topic, but I'm going to focus in specifically on those ideas of radiometric dating as their own application here in the next video. So see you for the next video.